Hello everyone, this is Bsc Secondary Analysis lecture. So today we are going to discuss one new concept, countability. Countability, that is countable and uncountable sets. So before going to start the countable and uncountable sets, so you must know what is meant by one-to-one correspondence between two sets. F from A to B is a function. And we say that A and B have a one-to-one correspondence. We say that A and B have a one-to-one correspondence. If there exists a function f from A to B which is 1, 1 and 1, 2. If there exists a function f from set A to B which is both 1, 1 and 2, then we say that there is a 1, 1 correspondence between the set A to B. So this is the one-to-one correspondence of two sets. Now, the definition of countable set. Countable set. Definition: a infinite set S, which is a subset of R, is said to be countable. Is said to be countable. Is said to be countable if it is equivalent to set of natural numbers, that is positive integers, set of positive integers, which is natural numbers. A set is said to be countable. An infinite set is said to be countable if it is equivalent to set of the positive integers, that is, it is equivalent to set of natural numbers. Or an infinite set which is a subset of R is said to be countable, is said to be countable if there is a one-to-one correspondence between S and N. That is, there must exist a function f from S to N which is both 1, 1 and 1, 2. And if some function exists from a set S to N which is both 1, 1 and 2, then we say that S is countable. S is countable. So this is the definition of a countable set. Now some illustrations. First, the set I of integers is countable. The set I of integers is countable. Now we know that I is nothing but -3, -2, -1, 0, 1, 2, 3. And we know that the set of natural numbers is 1, 2, 3, 4, 5, 6, 7, So we can introduce some function f from n to I which which is both 1 1 and 2. Then we map 1 to 0, 2 to -1, 3 to 1, 4 to -2, 5 to 2. We can find a map such that the image of 1 is 0, the image of 2 is 1, image of 2 is -1, image of 4 is -2, image of 5 is 2, image of 6 is -3, and image of 7 is 3, and so on. Like that we can find a function f from set of natural numbers to set of integers, which is both 1 1 and 1 2. Therefore, the set of natural numbers, set of integers is equivalent to set of natural numbers. Therefore, the set I of integers is countable. Second, yes is nothing but 1, 4, 9, 16 and so on. That is the squares of all natural numbers. Square of 1 is 1, square of 2 is 4, square of 3 is 9, square of 4 is 16, square of 5 is 25, like that. So we can define a function f from n to s such that f of n is nothing but n square. So this function defined from a set of natural numbers to a given set such that f of n is equal to n square, which is both 1 1 and 2, 1 1 and 1 2. Therefore, we can say that there is a 1 1 correspondence between set of natural numbers to this set. Therefore, this set is equivalent to set of natural numbers. Therefore, S is countable. Hence, we can say that S is countable. Is countable. This set is countable. Now third. Pn with the set of all polynomials a0 plus a1x plus dot 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 plus an x raised to n, where AR belongs to set of integers. Set of all polynomials of degree n have degree at most n. This set, therefore, now for a0 we have countable choices I, because I is countable. For a0 we have countable choices. A1 has countable choices, dot dot dot, an has a countable choices, and we know that the union of countable set is countable. Hence, Pn is countable. Pn is countable. Also, we can define a function f from I to Pn such that, Pn to I, hence the countable union of countable sets is finite union of countable set is countable. So for a0 we have countable choices, A1 for A1 we have countable choices, and for an we have countable choices. Hence this set contains countable number of polynomials. Hence Pn is countable. Now the set S for a comma b such that a comma b belongs to set of integers. Now for A we have countable choices, for B we have countable choices. Hence this set is countable because a comma b belongs to set of integers, and we know that set of integers is countable. Hence this set is countable. Now 4, 5, the set R is uncountable because we cannot find a function f from a set of natural numbers to set of real numbers which is both onto. Hence, set R is uncountable. Now an example I am going to discuss, which is very important. The set of real numbers, example, the set of real numbers in the closed interval 0, 1 is uncountable. Now we have to prove this. The set of real numbers in the closed interval 0, 1 is uncountable. So I am going to prove this by contradiction method. By contradiction method. So let this set is countable. Let the set 0, 1 is countable. Let this set is countable. So the set S, which is nothing but 0, 1, which can be written like this: 0 less than or equal to x less than or equal to 1, which can be written x1, x2, xn, dot, dot, dot. Because this set is a countable, we have considered. So we can write like this. Then, so each number in S, each number in S can have their decimal expansion like this: 0 point, a1, a2, dot, 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 a, dot, 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 where ai belongs to 0, 1, 2, dot, 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 9. So each ai belongs to these 10 numbers. Now for terminating decimal, we can write. So for example, 3 to 5. This is a terminating number between 0 and 1. So we can write this number as a 3 to 5, 0, 0, 0, dot, 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 or 0.3 to 4, 9, 9, 9, 9. So for these two numbers, represent 0.3 to 5. And for non-terminating number, there is no problem. For non-terminating number, there is no issue, because the representation of the number between 0 and 1 is like this. Now consider, define a function 1 from which is a n, that is set of natural numbers. 0 point a11, a12, a13, dot, dot, dot. Second, 0 point a21, a to 2, a to 3, dot dot dot. For third 0 point a, a31, a32, dot dot dot, and dot 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 this. So define the function. Because we have considered that each element of this set 0, 1 is like that, this. So we have defined the function. 1 goes to this number, 2 goes to this number, 3 goes to this dot dot dot. Because our domain is the set of natural numbers, and we have considered the set is countable. That's why we have written this. Now construct a set, or construct a number Now construct a number .b1, b2, bn like this. For if ai equal to 5, where for I 1, 2, 3 dot dot, and 5 if I is not equal to 5. Construct a number this, and this number does not belong to this above list, and observe that above number does not belong to the defined list, does not belong to the defined list. This implies that there are some numbers other than the numbers in the defined list. Hence, we got a contradiction that the function f is 1, 1. This implies that our assumption that the set S is countable, S is countable is false. Hence, we got a contradiction. Hence we arrived at a contradiction. That S is uncountable. Hence, the real numbers between the closed interval 0, 1 is uncountable. Hence the proof. Now, from this, we can also write A, B belongs to R. Then all intervals, closed interval AB, open interval AB, semi-closed or semi-open interval, These all are uncountable. These all are uncountable. For example, closed interval 0, 1, open interval 0, 1, semi-closed or semi-open interval 0, 1. So these all intervals are uncountable. That is, if a comma b are any two real numbers, then the interval, each interval that you have written is uncountable. Now, the set of rational numbers, example 13. Now example 30. The set of rational numbers in the closed interval 0, 1 is countable. The set of rational number in the closed interval is countable. That is, we have to prove that Q intersection 0, 1 is countable. Set of all rational numbers in 0, 1 means Q intersection 0, 1 is countable. Now we can write the rational numbers in 0, 1 as 0, 1, 1 by 2, 1 by 3, 2 by 3, 1 by 4, 3 by 4, 1 by 5, 2 by 5, 3 by 5, 4 by 5, and dot 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 like this. And define a function f from n to Q intersection 0, 1 such that 1 goes to 0, 2 goes to 1, 3 goes to 1 by 2, 4 goes to 2 by 3, 2 by 3, 5 goes to 1 by 4, 6 goes to 3 by 4, 7 goes to 1 by 5, and dot 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 like this. So there is a 1-1 correspondence between set of natural numbers and rational numbers in the interval 0, 1. Hence, the rational numbers in 0, 1 are countable. Hence, n and rational numbers in 0, 1 are equivalent. This implies that Q intersection 0, 1 is countable. Hence, we can say that Q intersection 0, 1 is countable. Now, theorem 13. If a function f from a to b is 1, 1 and b is countable, then A is countable. This theorem we need to prove. Now the function f from given function f from a to b is 1 and given that b is countable. B is countable. The function f from a to b is 1 and given that b is countable. So if the function f from a to b is 1 this implies that cardinality of a is less than or equal to cardinality of b. If the function, note that if the function f from a to b is a 1 then cardinality of a is less than or equal to cardinality of b. Where this notation denotes that number of elements in a is less than or equal to number of elements in b. So, and b is countable and the cardinality of a is less than or equal to cardinality of b, then which implies that a is countable. A is countable. A is countable. Also note that the countable word is used for if the set is empty, if the set is finite, and if the set is countably infinite. The word finite is used for these three conditions. If the set is empty, then we can say that this is a countable. If the set is finite, then we can say that the set is a countable. And if the set is countably infinite, then we can also say that the function is or the set is countable. So आजचं लेक्चर इथंच थांबूया. नेक्स्ट लेक्चर मध्ये नेक्स्ट कन्सेप्ट घेऊया. थँक्यू.